Okay, so let's do another session just focused on how to implement the shortest path algorithms that we've seen. These are actually quite easy algorithms, so I don't expect that this would take much time. Let me share my screen. Okay, so let's say I have this graph, and let's start with the Bellman-Ford algorithm. So remember, the Bellman-Ford algorithm basically found the distances from a fixed source point, right? So my input was a graph, and I also had weights on the edges, and my output was basically the distances from a given vertex u to every other vertex, right? And the way I did this was using a dynamic programming approach. So d of ik was the distance from vertex u to vertex I if I used at most k edges. And then we had this recurrence here as well. Okay, so let's implement this. Bellman-Ford.cpp. I'm going to start by reading my graph as usual. So let's say I first read the number of vertices and the number of edges. And then for every edge, I just read the two endpoints and the weight. So I read U, V, and O. Okay. And finally, let's say that I have a source vertex, and I'm reading that one as well. Okay. Now, here's what I wanted. I wanted to say that I have a distance, which is like the distance from U to I using at most k edges. So this was d of ik. And let's say my max n is something. Now I'm going to just create this array. So I'm going to have d, which is max n by max n. And again, d of ik is the distance from the source, from S, to I, if I can use at most k edges. Okay. Now, I have to initialize these things. So first of all, I want to set all of my distances to infinity. So let me have my infinity. Again, because of 2's complement, this is the biggest number that can actually fit in an integer. So let's see, how do I initialize this? I want everything to be infinite initially. So I say for I from, let's say 0 to n, it's actually 1 to n. That's fine. And for every k from 0 to n, d of ik is infinite. The only thing is that the distance from S to itself should be 0. So actually, yeah, here when I read S, I would say that d of S0 is equal to d of S1 is equal to 0. Well, actually, not this one, because maybe I have a self loop. But I cannot have negative self loops, right? So no, this was correct. And also when I see that I have an edge from U to V with weight W, I would say that d of, oh, can I say anything there? No, not really, I cannot do that. I have to just save my edges separately. Should I save it as a matrix? I can save it as a matrix actually this time, because I already have this huge matrix here. But let me go ahead and just use the same thing as before. So let's say that I have a list of neighbors. And let's say I also have the corresponding weights of edges. Okay. And I'm considering an undirected graph. So I say in the neighbors of U, put V, and the corresponding weight is W. And in the neighbors of V, add U, and then the corresponding weight is also W. Of course, if this were a directed graph, I wouldn't have these two lines. Okay, I've added all of these things. Now what? So I basically want to go over every edge, right? So this was my algorithm when I wanted to calculate d of ik. So the idea is that I want to reach vertex I with k edges. So I look at all of the predecessors of I, and I ask what is the shortest path with k minus 1 edges to any of these predecessors. So actually, maybe instead of this, it was better if I just had predecessors, right? So, but that's fine. Let's just call it an A. And anyway, I'm considering an undirected graph here, so it doesn't matter. All the neighbors are predecessors and all the neighbors are also successors. But of course, we remember that if this was a directed graph, I had to look at the predecessors, so I had to save the predecessors here. Okay, now my main algorithm. So for every k from 0 to n minus 1, I want to calculate the distance to every vertex I. So for every I from 1 to n. Now, this is our special case. Well, if k is 0, I've already put it there, but actually I could just put it here, right? So I could say if k is 0 and I is s, so the distance from the source s to I without any edges, it's just going to be 0. Otherwise, if k is 0 and I is not equal to s, d of ik is going to be infinite. Okay? Otherwise, I say my initial answer is just what I could get with k minus 1. So I would just say d of ik becomes d of I k minus 1. Right? And then I would just go over every predecessor j, and I would do this. So for every, let's say j is the index, j is 0, j less than neighbors of I, that's size, plus j, and let's say small j is the actual neighbors, is the actual neighbor, and the weight is this. Okay, so my d of ik becomes the minimum of whatever it is right now, and the distance to j if I had k minus 1 steps, plus the cost of going from j to I, which is just W. Okay. So this is how I would update all of these things. This is basically a direct implementation of what I wrote here, which was my dynamic programming. Right? And finally, in the end, let's say that for every I from 1 to n, I just write d of I n minus 1. And let's say this is distance to I is this. Okay, let's compile this. And let me copy this thing. Okay. And as you see, nothing worked out. Now, what's the problem here? Why didn't it work out? Well, actually, it has a lot to do with this plus here, right? So if I have this infinite value here, which is the largest value that fits in an int, I cannot sum it up with anything, right? So here I have to say this happens only if d of j and k minus 1 was not infinite. And of course, w was also not infinite, but w is never infinite. So if I have that, and now let's see if this works. Yes, okay. So it says distance to 1 is 0, distance to 2 is 2, distance to 3 is 3, distance to 4 is 7. Yes, okay. Distance to 5 is 4, distance to 6 is 6. It seems it's correct. Okay. Now, of course, we could also use Dijkstra. And remember, we have already implemented Dijkstra. So I guess if I just compile the codes that we had for Dijkstra, and if I give it the exact same input, it's going to give me the exact same output, right? So the distance to 9 is 7, for example, the distance to 9 is 7 years. So, but the whole point of using Bellman-Ford was because Dijkstra doesn't work correctly in presence of negative weights. Okay, so let's say, for example, that here instead of 4, I had minus 4, right? Let's see what Dijkstra gives us. So I'm changing the weight of the edge from 2 to 7 to minus 4. Again, let me compile Dijkstra and let me give it this input. It's exactly that graph, except that the weight of the edge from 2 to 7 is now minus 4. Okay. Now, what's happening here? The distance to 1, it says is 0. The distance to 2 is 2. Okay. The distance to... Oh, in this case, it works, right? Yeah, let me see. How can I find an example where Dijkstra doesn't work? This wasn't a good example. Let's see. So I'm going to 2 with distance 2, but I want to have a better distance. So let's say it would be better to do 7 minus 5 minus 1. And here, instead of 6, let's put a 0. Okay. So let's do it with this one. So the weight of the edge from 2 to 3 is now 0. The weight of the edge from 3 to 5 is minus 1. The weight of the edge from 4 to 5 is minus 5. Okay. Do I have a negative cycle? Hopefully not. Okay. So now, what is the shortest path from 1 to 2? I can go 2 here, distance of 2, or I can go 7, 2, 1, and 1, basically. So the distance from 1 to 2 is actually 1 in this graph. So let's see what happens. I'm going to compile Dijkstra. I'm going to give it this graph. So this is just the same graph. I just made the changes. And as you see, it says that the distance to vertex 2 is 2, which is wrong, because Dijkstra cannot handle negative weights. But now let's do this with Bellman. And let's give it the exact same thing. Oh, distance to 1 is minus 16. What's happening? Did we do wrong here? Oh, yeah, the problem is because, oh, yes. So we actually do have negative cycles here. And the problem is because this is not a directed graph. So it realizes that it can go here and then just keep doing this. So yeah, this wouldn't work on undirected graphs if you have a negative weight, because in an undirected graph, if you have a negative weight, that negative weight is also a negative cycle. right? So let's actually make our graph directed. So let me do this, 1 to 2, 1 to 3, let's say I need this like this, 3 to 2. And let's just have this part of the graph. I don't want the rest of it. So if I have only that part, I have 5 vertices and how many edges? 1, 2, 3, 4, 5, 6 edges. So I have an edge from 1 to 2 with weight 2. I have an edge from 1 to 3 with weight 3. I have an edge from 1 to 4 with weight 7. I have an edge from 3 to 2 with weight 0. I have 4 to 5 with weight -5. I have 5 to 3 with weight -1. Okay, and my starting vertex is 1. So yeah, funny point, if you have negative weights in an undirected graph, there are already negative cycles because I can just go over the same edge back and forth. I wasn't paying attention to that. So let's say my graph is directed now. So that means that when I'm doing these neighbors, I have an edge from U to V. And since I want only predecessors, I'm going to do this. I'm going to only add it in V. Okay. Hopefully this works. If I haven't made any more mistakes, let's run this and let's give it this input. Yes. So as you see here, it says that the distance to vertex 1 is 0. The distance to 2, it doesn't say it's 2. It figures out that this path is actually better. And so the distance to 2 is 1. It's better to go this way. But now, if I did the same thing with Dijkstra, it wouldn't find out. So if I gave the exact same input to Dijkstra, it says the distance to 2 is 2, which is wrong. Again, so Dijkstra cannot handle negative weights. But for Bellman-Ford, you can also have negative weights, but keep in mind that you cannot have negative cycles. So if you have an undirected graph, having negative weights would be the same as having negative cycles. So be careful about that. Okay, so this is Bellman-Ford. Let me go back to my original graph. No negative weights. So 2 to 3 has a weight of 6. 3 to 5 has a weight of 1. 4 to 5 has a weight of 1. 5. Okay. So I went back to my original graph now, and let's do the other algorithm that we saw. So we saw Bellman-Ford. Oh, by the way, before moving forward, we can make this better, right? So here's the thing. The first thing I would notice here is that I don't really need this second part, right? So instead of having this second part, I can just have a single array D that only has Di, and Di is the distance from S to I if I can use at most K edges. But what if I use now a little bit more? It's not like I'm going to get a distance that is smaller than the overall distance, right? So in that sense, you can go back and watch the lecture for the proof for why I don't need this. But in that sense, we can basically save some space here. So let me do another version of this Bellman-Ford. So let's say I take Bellman-Ford and I call this Bellman-Ford space saver. And here, what I'm going to do is that I just don't keep track of the second part of my DP. So the second coordinate, I'm just going to ignore it. Here, of course, I don't have a second coordinate anymore. Here, I'm just going to remove the second coordinate. And as I said before, everything is going to work out. Now, why is this correct? Because anyway, when I'm looking at this D of J here, d of j is going to have a value which is between d of jk and d of jk minus 1. But no matter which one of them you put here, your final algorithm is going to be correct. And here I don't even need this because they're the same now. Okay, and this is just d of I. So let me do this. Bellman-Ford space saver, that's CPP. Line 45, I still have K. Okay. Okay. And now I'm going to give it the same graph. And as you see, it's giving the same values. And I can give it also the big graph that we just saw. These are hopefully also the same distances. I don't really remember it. It's fine. Okay, so this is a space saver version of it. But now let's look at this space saver version. What is it actually doing? It's basically saying, I'm gonna start doing this for n-1 iterations, or for n iterations. So that's the k, goes from 0 to n-1. And every time, the only thing that it's doing is that it says, if there is an edge from I to j, update the distance of I by saying that the distance to I is at most the distance to I, or the distance to j plus the weight of the edge between them. So this is what the textbook CLRS calls relaxation. So it's relaxing the edge from I to j. It's saying that whatever distance you knew to vertex I before, update it by checking if it's better to first go to j and then take the edge from I to j. So basically, all our algorithm is doing here is that it's going over these iterations, n iterations, actually n-1 is enough, and then it's just relaxing every edge in every iteration. So I could have just coded it like that, and that would have been even easier. So let me just copy this, and let me call it Bellman-Ford simple. That's CPP. Okay. Now in this one, I'm not going to keep neighbors. I'm just going to keep a set of edges. Okay. So again, I'm going to define an edge as a pair. Let's say something like this. I'm going to say U is first dot first, V is first dot second, and W, or weight, is basically second. Okay. And I'm just going to have a vector of edges called E. And every time that I read U, V, and W, I just say push back this edge into E. So E dot push back the edge from U to V with weight W. Okay. Now I said that here all I'm doing is basically relaxing all the distances. So paste this. I'm gonna say all the distances are infinite. Oh, I didn't need this for either. I forgot to remove this from the previous code. Please remove it from the previous code too, because all it's doing is going over the same array and setting it to infinity, of course. And here I'm going to say that my current distance to S is 0. And then for n times, I'm just going to relax all of the edges. So I say for every edge E in E, the distance to its endpoint, to E dot V, becomes the minimum of whatever distance I had to its endpoint right now, and the distance to its starting point plus its weight. Okay, E dot W. And again, I should do this only if these distances are not infinite. So if the distance to E dot U is not infinite. And that's it. This is also an implementation of Bellman-Ford. And as you see, like the main part of the algorithm is literally 5 lines. And this will also give us the same results. So Bellman-Ford simple.cpp. Let me give it the same graphs as before. So I give it this small graph. You see that it produces the same distances. And I can also give it the big graph. This one again produces the same distances. Okay. So this is an easy way of implementing Bellman-Ford. If you don't want to really think of Bellman-Ford as dynamic programming, you can just think of it as having n iterations, n-1 iterations, and in each iteration, just relaxing every edge. And this also works. Okay. So that's all for Bellman-Ford. Now that we've seen how to do this, we talked, of course, about a bunch of other algorithms as well. We talked about the algorithm that does matrix multiplication. That would also be interesting, even though its runtime is more than Bellman-Ford by log n factor. I'm not going to implement that one. We also saw Johnson's algorithm. And remember, the idea in Johnson's algorithm was that I have a graph, but in this graph, some of the weights are negative. And as we've seen in this session, Dijkstra doesn't work if you have negative weights. And I want to find the distances from every vertex to every other vertex. So instead, what I do is I first convert it to a different graph such that all the weights are non-negative so that I can apply Dijkstra. And the way I did that was by just adding a new vertex and adding edges of weight 0 from that vertex to every vertex, and then computing the distances from that vertex using Bellman-Ford, and then creating this new graph, and then doing n Dijkstras. Now, because I've shown you how to code Bellman-Ford and how to code Dijkstra, I'm not really going to do Johnson. This is just a combination of these two. Instead, let me go and do Floyd-Warshall. So remember, the idea in Floyd-Warshall was that we're also going to do a dynamic programming. This time we want to find distances between every pair of vertices. So for every I and every j, I want to know what is the distance from I to j. And the way we did this was that we defined a dynamic programming like this, so dp of I, j, k, and this was the cost of the shortest path from I to j. But instead of saying how many edges I can have in my shortest path, I'm just going to limit the internal vertices that can appear. So I'm just going to say only the vertices from 1 to k can appear as internal vertices. And then we saw that we have this really nice and easy recurrence. And we saw that we can code it like this. So I'm just going to do this now, Floyd-Warshall. Actually, let me just... Should I copy the previous one? No, let me just write it again. So I'm just going to call this Floyd-Warshall.cpp. And I'm just going to read all the vertices and edges. So read n and m. And for, I don't need the number of edges, so I can do something like this. I read u, v, and w, so there is an edge from u to v with weight w. Okay. So I have only these things, and let's say I have my max n here. I'm going to put my max n pretty small here because I'm going to create an array which is max n by max n by max n. So it's max n cube. So I'm going to have my dp, or my distance, basically, which is like this, max n by max n by max n. And initially, I have to basically put everything to be infinity. So I will look into that. So I say for every k from 0 to n, okay, and for every I from 1 to n, and for every j from 1 to n. So I want to calculate dp of ijk, right? So this is the shortest path from vertex I to vertex J that can only have the vertices from 1 to k as internal vertices. Now, the first case is that if k is 0, what happens then? I have to just write a special case here. If k is 0, well, this is actually pretty easy, right? So the distance from a vertex to itself is going to be 0 if I cannot use any other vertex as internal vertices. And the distance from I to j is just going to be the weight of the edge, okay? So actually, when I'm reading this, I can already say something like this. I can say dp of uv0 is w, and dp of vu0 is also w. Again, I'm assuming that I don't have a directed graph. If it's directed, of course, you put only one side of it. And the other thing I have to do for k equal to 0 is that dp of everything with itself and 0 is 0. So actually, let's say my k starts from 1, and instead I'm just going to say for every I from 1 to n, dp of I 0 is 0, okay? And now here, I'm basically saying for every k, and so k is the limit on which vertices I can use as my internal vertices. Now, I want to calculate dp of ijk, right? So here's the thing. If I want to go from vertex I to vertex j, and I can only use the first k vertices as internal vertices, I'm either going to use vertex k or I'm not going to use vertex k. Now, if I do use vertex k, then I have to go from vertex I to vertex k, but I can only have the first k minus 1 vertices as my internal vertices. And then I have to go from vertex k to vertex j, but I can only have the first k minus 1 vertices as my internal vertices. Okay, so that's the case when I'm using vertex k. So I have to take the minimum of this. And with the case when I don't use vertex k, which just means that I'm only using the first k minus 1 vertices. So this one is just dp of ij k minus 1. That's it. That's all of Floyd-Warshall. And then let's say for some reason I want to print the distances as well. So I just say for I from 1 to n, and for j from 1 to n, just write dp of ij n slash t at the end. Yes, okay. So this should print all of the distances. Okay, Floyd-Warshall.cpp. This graph is a bit too big, so it might take some space. Okay. So as you see, we have a bug. I don't know how I have a bug in such a simple thing. Let's see what's happening. So I'm reading UMV, dpUV0 is W, dpVU0 is W. For I from 1 to n, dpii0 is 0. Okay, for k from 1 to n, I from 1 to n, j from 1 to n, dpijk, ikk minus 1 plus dpkj. Oh, yeah, I forgot this. Well, of course, everything is initialized at 0. So of course, it's just going to give you 0. I have to initialize everything. And so let's say we initialize everything to plus infinity. So I'm just going to say for I from 0 to max n, for j from 0 to max n, for k. I mean, I could have done it in the 3 for loops below as well. It doesn't really matter. It's just the initialization. So I'm just going to say dp of ijk is some big number. Okay. This should work now. Yes, okay. So as you see, these are the distances from vertex 1, the distances from vertex 2, the distances from vertex 3, and so on. And what is that? Okay, so this is actually 0. I pasted this one. Sorry. So when I was pasting the input, let me do this again, because this was the input that I was using from before. So this is my input. And as you see, it's saying that the distance from 1 to 1 is 0. So on the diagonal, we only have zeros. Okay, so this is Floyd-Warshall. But just like the case of Bellman-Ford, I can simplify this. So let's say I do Floyd-Warshall simple.cpp. And the simplification is, again, that I don't really need to keep track of this k, right? So again, if you think about it, dp of ijk is the length of some path that goes from I to j, okay? So imagine that I don't have this k. If I don't have this k, then the answer that I'm going to get is not going to be smaller than the shortest path from I to j anyway. dp of ij is going to be at most the shortest path. On the other hand, when I'm calculating this, here instead of dp ij and k minus 1, it might be that I'm already putting, instead of this k minus 1, it might be that I'm already putting k. So I'm not going to get anything worse than the shortest path, and also I cannot get better than the shortest path. So I don't really need this last part, right? So instead of this, I can just have a dp that only has I and j, and I don't have the k. I initialize it. And here, I don't need the 0. And okay, here I don't need the 0 either. And here I just say dpij, dpik, dpkj, dpij. Okay, now if you look at this, this is also very intuitive. All this is saying is that I do n iterations, just like Bellman-Ford, but in every iteration, what I do is that I say, if I want to go from I to j, if I want to find the distance from I to j, I already know some distance, but maybe it's better that I first go from I to k and then I go from k to j. That's all this is saying. It's very intuitive, right? And then I would just print my answer. This is going to give me exactly the same answer as before. Give it the same input, it gives the same output. Again, this just saves some space, and it's also easier to code. I mean, you can easily think about this and code it. Again, we've talked about this when we were talking about the dynamic programming that is actually behind Floyd-Warshall, and the order of these for loops really matters. So if you write for I, for j, and then for k inside, your dp will not work out. You have to make sure that the k is on the outside. And this has to do, again, with the order of our subproblems. Remember when we were defining our subproblems, I was saying that the dp of ijk is the cost of the shortest path from I to j that only uses the first k vertices as internal vertices. But this dependent on the dp with value k minus 1. So this one has to be calculated before this one. Now, of course, we simplified the implementation here, and we argued that it remains correct even if I remove that last coordinate. But again, even though it remains correct, you have to make sure you're computing them in the right order. If you switch the order of the force, you will not get the right answer. Okay, that's it. I'll see you soon.